Welcome back, guys. Today we're going to dive into the subject of addition of fractions. What we're going to see is that addition of fractions is not too bad. It's going to be similar to ordinary addition, but with additional steps. And interestingly, if we understand the topic of multiplication of fractions, then the addition of fractions is just multiplication of fractions with more steps, okay? And we'll see exactly why that's the case. But before we get to that, let's just recall the basic definition or the basic premise of a fraction to begin with. Uh, we started off this section by discussing that the idea that a fraction is a kind of tool of sorts that's usually used to measure objects that exist in the physical world that are of a non-standard size, if you will. Some things that are a little bit too small and or things that are a little bit larger than perhaps what we anticipate, and so they don't lend themselves to a size that is nice, i.e., a whole number, and instead it might be a little bit larger than a whole number or a little bit smaller than a whole number. And how we deal with measuring these objects out, regardless of what the object might be, is that we would take some sort of a measuring device that usually is of a standard size. Back in the day, it was a cubit. Today, we have feet, meter sticks, and or yardsticks. And what you start to do with these measuring tools is you partition them or you cut them into small equal parts. And so, for example, if you had an object that instead of being 1 unit long was in fact half the length of of the unit of measure that you were dealing with, then you could take the ruler or the yardstick or the meter stick, and if you had half of a foot, for example, that you were measuring out, you could just cut the uh, measuring stick in half into two equal pieces. And if you took one of those pieces, you would be able to measure the object that's exactly 1/2 of a foot. And if you had an object that was even smaller than 1/2 of a foot, maybe it was 1/3 of a foot, then you could cut a foot into three equal parts. You could take one of the pieces of three, and you would be able to measure that object out. If you had an object that was even smaller that you needed to measure, maybe it was a fourth of a foot exactly, you could take w- a a foot, a measuring stick rather, and cut it into four equal pieces and take one of those pieces. And the idea was that even if the object was, say, bigger than 1/2, maybe it was 1/2 and then some change, right? You could take the 1/2 stick that you have, and if you had an object that was even just a wee bit bigger than 1/2, maybe it was exactly 1/4 of an inch larger than 1/2, then you could take the 1/4 of an inch and and stack it on top of the 1/2 of an inch, or you could take the 1/4 of a foot and stack it on top of the 1/2 of a foot, whatever the unit of measure happens to be. You can kind of stack these measurements on top of each other until you're able to measure out the size of the object in question. Okay? But now the question is, what would this distance be equal to? If we measured out this object and maybe it was 1/2 of a foot plus 1/4 of a foot, okay, how many feet would this distance be? Well, obviously we can say, well, it would be 1/2 of a foot plus a fourth of a foot, right? But what does that actually mean? Okay, that's the question we're going to answer today. So recall that as we were defining certain properties of fractions, we said that, well, if you had cut a foot into pieces of three and you took 1/3 of a foot and you stack a third of a foot with another third of the foot, right? Well, how many thirds of a foot do you have? And it stands to reason that you should have 2 thirds of a foot because you have exactly 2 pieces of 3. If you cut the foot into 3 equal pieces and you took one piece and stacked it on top of another piece of the foot that had been cut into 3 pieces, you should have now 2 pieces of 3. And it's very similar to just asking yourself, well, if I've got 1 apple plus 1 apple, how many apples do I have? Naturally, you would have 2 apples. And if you have 1 orange plus 1 orange, how many oranges do you have? We would say we have 2 oranges. Now, what we're saying here when we start stacking thirds of a foot on top of each other is we're saying we have 1/3 plus 1/3. How many thirds do I have? I have 2 thirds. And it makes a lot more sense when you actually write it out in the form of a word, because people can then see how equivalent saying the word third would be to saying the word apple, right? You might have 1/3 of an apple, and if you added it with another third of an apple, you would have 2 pieces of an apple that had been sliced into 3 equal parts, or said another way, 2/3 of an apple, right? Similarly, if we had taken a foot and we had cut it into 4 equal pieces, we cut it into fourths, and you start stacking fourths on top of each other, you might ask yourself, well, how many pieces of 4 do I have? If you have 2 pieces of 4 and you add those together, you would say that you have 2/4. So we'd say 1/4 plus 1/4 gives me 2 pieces of 4. If I had another 1/4, or said another way, you have 2/4 plus 1/4. How many pieces of 4 do you have? Well, you have 3 pieces of 4. Because you already had 2 pieces of 4 earlier, so if you took another piece of 4 and you stacked it with 2 pieces of 4, you should now have 3 pieces of 4. And naturally, if you took 3 pieces of 4 and you added another 1 piece of 4, and you asked yourself how much you have at that point, we would say we have 4 pieces of 4. Here's the issue. Here's the issue that we encounter. When we're adding numbers that have what is known as a common denominator or common base, okay? 3/4 and 1/4 have a common denominator or common base for the fraction because both fractions have 4 in their denominator. We can add those pieces together straight across the top, and the answer actually makes sense. In this case, we added 3 with 1, giving us 4, right? And earlier, when we took 1/4 with 1/4, we added across the top because there again, we have a common denominator. And when we added across the top, we found that we had 2/4. And when we added 2/4 with 1/4, there again, you had a common denominator. And you were able to arrive at 3/4. The denominator or the base may be thought of as the type of measuring tool that you're using. So when we're measuring using fourths of a foot or fourths of an inch, it makes sense that we can take 1/4 with 1/4 and get 2/4. It makes sense that if you have 2/4 and add 1/4, you get 3/4. And it makes sense that if you have 3/4 with 1/4, you get 4/4. And understanding that the base is just the type of measuring tool It then also makes sense that 1/3 plus 1/3 gives you 2/3. And if you add 2/3 and added another third, you should get 3/3, right? Because 1/3 would similarly be just a different type of measuring tool. You're measuring in thirds of a foot or thirds of an inch instead of a fourth of a foot or a fourth of an inch, right? So it makes sense that you should be able to add those pieces. But here's the issue over here is that you have 1/2 of a foot and you're adding it with 1/4 of a foot. The problem is we need the same measuring tool in order to measure out how many pieces of a foot we actually might be dealing with. And so this is the challenge. We need to develop a system in order to find what's called a common denominator between the fractions. But how do we do that? One way to think about finding a common denominator is to consider a candy bar. When dealing with fractions, it's often useful to try to go back to candy bar examples whenever you get confused. If we were adding 1/2 with 1/4, consider actually cutting a candy bar into 4 pieces and cutting another candy bar into 1/2 pieces. And then taking each of those slices. Here's my 1/4 piece. Here's my 1/2 piece. Okay? And if we were to add them together, I would just take this 1/2 piece and put it in a stack with the 1/4 piece, right? Now, if we actually wanted to make sense of that number, though, we would need to take our candy bar and instead of cutting it into 1/2 or 1/4 pieces, we would actually have to find fractional piece of the candy bar, which would be equivalent with taking 1/2 of that and taking 1/4 of the other one and adding those together in such a way to where you could actually make sense of the number. And the trick to this is if instead of, say, slicing the candy bar into 1/2 pieces and 1/4 pieces, we actually cut the candy bar into 8 pieces. Okay. I hope you guys can see that the 1/2 of the candy bar would be the same thing as if you had taken 4 pieces of a candy bar that had been cut it into 8 pieces. And if you had done the same thing with 1/4 of a candy bar, if you had cut it also into 8 pieces, then it's pretty straightforward to see that 1/4 of the candy bar would be the same thing as taking 2 pieces of a candy bar that had been sliced into 8 equal parts. Okay, so then we now have a new problem. 4/8 plus 2/8. What would that be equal to? Well, what we know is we need to just stack the pieces of our candy bar in a pile. So we have 4 pieces and 2 pieces of a candy bar sliced 8 ways. And of course, that naturally gives us a candy bar that is 6 pieces from 8. So we would say that 1/2 plus 1/4 is the same thing as taking a candy bar that has been sliced into 4/8 of a pieces, adding it with 2 pieces of a candy bar that has been sliced 8 ways. And when you add those together, you get 6/8 of a candy bar. At this point, it's important to note that when we add fractions together and we get an answer, 6/8 in this instance, this 6/8 isn't in fact a correct answer because 6 uh, is divisible by some quantity and 8 is divisible by some quantity. In this case, they're both divisible by 2. And so what would happen is if you did prime factorization of 6, you'd find that it was the same thing as 2 times 3. And if you did a prime factorization of 8, it's the same thing as 2 times 2 times 2. So this 6/8 is actually 2 times 3 all over 2 times 2 times 2. And what we learned before is that whenever you have these prime factors stacked on top of each other, each of the prime factors will simply divide out. And so you should be left with a new candy bar that has that is equivalent to 3/4. So it turns out if you took 1/2 of a candy bar and added it with 1/4 of a candy bar, you would be left with 3/4 of a candy bar. Interestingly, we might have gotten an answer to this problem statement a little bit faster if we had considered perhaps instead of, say, slicing the candy bar into pieces of 4th, if we had, or sorry, pieces of 8, if we had instead taken our 1/2 of a candy bar and sliced it into pieces of 4. Here's my candy bar that's sliced into pieces of 4. Here's my 1/4 piece. If I had taken the top candy bar and we sliced it into pieces of 4, you'll see that the 1/2 piece is exactly equal to 2 pieces of 4. Here's my 1/2 piece, what we had before, right? 1/2 of a candy bar would be just one piece from the candy bar that had been sliced into 2 equal pieces. But if we had taken each of those half pieces and cut it in half as well, you'll see that you have 4 equal pieces of the candy bar. And if you had taken 2 of those pieces of the candy bar, that would be the same thing as your 1/2. And so now you can see why we got the answer 3/4, because it turns out that when we added 1/2 with 1/4, that was the same thing as taking 2 pieces of 4, adding it with 1 pieces of 4, which gives you 3 pieces of 4. Now, the question that students will naturally have at this point is, well, this is all well and good, but how do we find the common denominator that we need to use in order to add the fractions in the first place? And the short and simple answer to this is that there are 2 techniques. We might use the multiply by the opposing base method, or we can use what is known as the LCM method. Now, if we use the multiply by opposing base method, this is fairly straightforward, and it's probably the easiest method for students to remember. So definitely take notes at this part. If we had wanted to say take 1/2 and add it with 1/4, here's my 1/2, I'm adding it with 1/4. One of the easy ways to do this would be to multiply by the opposing base. And what that means is you're going to take your 1/2 or your first fraction that's on the left. You're not going to do anything to it. You're just going to rewrite it on the line below. And I want every student to write out their fraction addition just like I'm doing. You're going to write out the problem statement. If you're given 1/2 plus 1/4, you're going to do that on the first line. You're going to always drop down to the next line. Rewrite the first fraction on the left. Don't do anything to it. You're just going to take that 1/2 in this instance. You're going to rewrite it on the next line down. And then what you're going to want to do is you're going to take the opposing base of the fraction, i.e. the base of the fraction that's on the right being added with the 1/2 in this instance. And that happens to be 4. And what we're going to do is really, really clever. We're going to take the 4, we're going to construct a new fraction, in this instance 4/4, and we're going to multiply this new fraction by the first fraction, 1/2. And then we're going to do the same thing to 1/4. We're going to take 1/4, we'll rewrite it down below. We're not going to do anything to it, but we are going to take its opposing base, which happens to be 2 in this instance. We'll construct a new fraction, in this instance 2/2, and we're going to multiply 2/2 with 1/4. Now, students, what you need to know is that there are many different ways of being able to add fractions that you might find on the internet. But the multiply by the opposing base method, if you just write it out, you just get into the habit of writing out this particular step, will always work. Is it more work? Yes. Will it always work? Yes, it will always work. Will it necessarily be the fastest way to get the answer? Obviously not. But again, we need a method that always works that we can remember when we're going into our later algebra class. We don't need to be it's better to memorize one method and really master it than to memorize 1,000 different methods and you can only partially remember those methods going forward a year from now, right? So memorize this. If you're not going to memorize anything at all in this class from here on outwards, definitely know how to do this because this is going to be a lifesaver going forward. And I still see students that are in the Math 950 section and the Math 1100 section. If they're messing up anything, they are messing up this step because they want to do it in their head. They don't want to write things out. They don't want to do any accounting. They refuse to write down anything on their paper. So the students that write things out, they're the ones who get the A's naturally. The students that don't write anything out, they're not going to, their grades are going to suffer. What we're going to do now is we'll have 4 times 1, which gives me 4. 2 times 4 gives me 8. 1 times 2 gives me 2. 4 times 2 gives me 8. You'll see that we have a totally new sequence of fractions that are being added together. And students might ask me, Mr. B, these fractions look nothing like the fractions above. How do we know when we get the correct answer? And my answer to those students is twofold. On the one hand, did you set this up correctly? Right? Did we set this up correctly? And if the answer is yes, then the next question would be, did you do multiplying across the top and across the bottom correctly? And if the answer to that is also yes, then you have the correct answer. Okay, simple as. Now, uh-oh, what did I do? Uh-oh, I think I did something to my page. I don't know what that is. Okay, uh-oh, I'll go down. I don't know why it's doing that. There was one step that we did skip, and it is the step that demonstrates how we are multiplying our numbers out. It would be good to write this step out down here before you go and multiply your fractions together. But is it totally necessary? No, it's just more for your accounting purposes than anything else. So on the one hand, you can always go back and you can start to just write more steps in order to convince yourself that in fact you're doing things the correct way. And yeah, sometimes it's also a matter of practice. Like how many times did we practice this particular technique in order to develop confidence that our answer is correct? That would also be another way to just, ingrain into yourself that you are in fact doing the correct sequence of operations. Now, at any rate, the long and the short of it is, once we get to this step and we have a common denominator, you see that we have 8 in our denominator here. So we have a common denominator. At this point, you're going to add across the top. You're going to do 4 plus 2, give you 6. And we're going to need to do some fraction reduction. Again, use prime factorization on the top and on the bottom. And then cancel out factors that are in common. Let's do another example. Suppose I want to take 3/7 and add it with 4/3. And I want to know how much this is. All I'm going to do is I'm going to write out my 3/7 on the line below. I'm going to take 3, which is my opposing base, and I'm going to multiply it by 3/7. Then I'll take 7, that is my opposing base, and I'll multiply it with my first fraction, 4/3. Now, it should be known to students that these numbers, 7/7 and 3/3, aren't just like magically appearing. Okay. It seems as though these numbers are just magically appearing within our equation, but you should realize or should take a step back and understand that, if you have a statement like 2 is equal to 2, you can't just randomly create new numbers and multiply them with one side of the equation and not the other, right? Like if I took, say, the number 3 and multiplied it on the left side of my equation, then I'd get 6. And because I didn't do anything to my right side of the equation, I would get this nonsensical statement 6 is equal to 2, and 6 is certainly not equal to 2, right? So it's not what we're doing here is we're not creating new numbers just out of nowhere that we're multiplying with 4/3 and 3/7. But in fact, what's happening is we are cleverly exploiting what is known as the identity law of algebra. And that is to say that whenever you take 1 and you multiply it by a number, or a number multiplied by 1, you get the same number back. Recall that fractions are the same thing as representing a division operation. So when you say 3 divided by 3, this is the same thing as 3 little division symbol 3. And 3 divided by 3 gives you 1. So what's really happening is you're multiplying 1 by 3/7. And because 1 times anything is just that something, 1 times 3/7 gives you 3/7. But the clever thing about this is you're multiplying 1 in such a way as that we can convert the denominator of whatever fraction we're looking at to be something else so that we then have common denominators. Okay, so we're going to take that 7. Now we're going to multiply with 3. We're going to take 3, we multiply with 3. So we have 3 times 3 on top, 7 times 3 on bottom. We're adding this with 4 times 7 on top, 3 times 7 on bottom. 3 times 3 is 9. 7 times 3 is 21. 4 times 7 is 21. I'm sorry, 28, rather. And 3 times 7 is 21. Now you're going to add everything across the numerator. So you get 9 plus 28. 9 plus 28 gives you 37. So we should have 37 over 21, and that would be our answer. There are some limitations to the multiplied by opposing base method, and it generally starts creeping into the problem statement whenever you start dealing with situations where you might have either 2-digit or 3-digit or 4-digit fractions that you're trying to add together. It turns out that if we are adding 3-digit or 4-digit fractions together, even 2-digit fractions, there are going to be so many different multiplication operations that we have to go through that it just becomes a kind of a pain in the butt to use the multiply by opposing base method, but it will in fact still work. So consider, for example, just as a small limited example, suppose you had 27 over 59, and you're adding this with 34 over, and let's not do 59. Let's do a nice number. In fact, we'll do 84. And we'll do 34 over 96. Another nice fraction. Now, and we wanted to know what this is, naturally. Now, if we want to be able to add these fractions together, we've got to multiply by the opposing base. So I'm going to take 96, which is the opposing base of my first fraction, and I'll multiply on the top and the bottom of the second fraction. And I'll actually change my color here just to illustrate that. So 96 is the opposing base to 27 over 84. 27 over 84 doesn't change, but you're going to take 96, you'll construct a new fraction, and you're going to multiply that with your first fraction. And then we're going to do the same thing to the second fraction. We'll take 34 over 96. We're not going to do anything to it, but we will multiply that with 84 over 84. All right, voila. So then what is this equal to? Take a deep breath. It's take a deep breath. I know some students are like, "Oh my God, what in the world?" It's all good. It's all good. It's just multiplication operations. We are going to multiply across the top and the bottom. We need to multiply 27 and 96. We need to multiply 84 and 96. We need to add this with 34 times 84 all over 96 times 84. Because remember, we multiply fractions across the top and the bottom. So what does this equal to? Well, we are going to have to go to the side of our page and do quite a bit of multiplication operations. And this can be a bit time intensive. And I am going to actually rewrite this multiplication as 27 on bottom and 96 on top. All right, so 7 times 6 gives you 42, carry the 4. 7 times 9 is 63, plus 4 gives you 67. Drop your 0. 2 times 6 is 12, carry the 1. 2 times 9 is 18, plus 1 is a 19. Add everything together. 2 plus 0 is 2. 7 plus 2 is 9. 6 plus 9 is 15. Carry the 1. 1 plus 1 is 2. So we get 2, 5, 92. On top. And now we need to do 84 times 96. 4 times 6, 6 12 is 18, 24. So we drop the 4, carry the 2. 4 times 9 gives you 36, plus 2 gives you 38. Drop a 0. 8 times 6 should be 48. Carry the 4. 8 times 9 gives you 72, plus 4 gives you 76. Add everything together. 4 plus 0 gives you 4. 8 plus 8 gives you 16. Carry the 1. 1 plus 3 is 4. 4 plus 6 gives you 10. Carry the 1. 1 plus 7 is 8,064. So there we go. 8064 on our denominator. 8064 on this denominator. And now we have one more multiplication operation. 34 times 84. 4 times 4 is 16. Carry the 1. 4 times 8, 8, 16, 24, 32. Plus 1 gives you 33. Drop your 0 down. 3 times 4 is 12. Carry the 1. 3 times 8, 8, 16, 24. Plus 1 gives you 25. So if we've done everything correctly, we should have 6 plus 0 is 6. 3 plus 2 is 5. 3 plus 5 is 8. So we get 2, 8, 56. Okie dokie. So now is the easy part. We know that whenever we're adding fractions and we have a common base, we simply add across the top. So I don't want you to do anything with denominators. We can just take a little bit of a sigh of relief. All we're going to do is we're going to denote the fact that we are going to, in fact, add these fractions by taking 2592 and adding it with 2856 all over 8064. So now we're going to calculate what that is. Okay, 2592 added with 2856. 6 plus 2 is 8. 9 plus 5 is 14. Carry the 1. 1 plus 5 gives you 6. 6 plus 8 gives you 14. Carry the 1. 1 and 2 is 3. 3 plus 2 gives you 5. So we should have 5, 4, 4, 8 all over 80, 60, 4. Now, naturally, we are not done here. We are not done here. We would have to then simplify our fraction at this point, assuming that the fraction could be simplified. In this instance, our fraction certainly can be simplified because your numerator and denominator are both divisible by 2. On the other hand, you might try to determine if there's a number that's bigger than 2, which might divide the numerator and denominator. But given that we can indeed divide it by 2, let's just, we'll not be lazy. We will, in fact, just divide it by 2. 2 goes into 8 4 times. 2 goes into 0 0 times. 2 goes into 6 3 times. 2 goes into 4 2 times. So you would be able to reduce 8064 to 432, 4032. So 4032. And then we would be able to reduce 5448 to 2 goes into 5 2 times. 2 times 2 is 4. Subtract. You get 1. Drop your 4 down. 2 into 14 goes 7 times. 7 times 2 is 14. Subtract, you get 0. Drop your 4 down. 2 into 4 goes 2 times. 2 times 2 is 4. Subtract, you get 0. 2 goes into 8 4 times. So now we have reduced our numerator to 2, 7, 24. All right. And assuming that we don't make a mistake, we can just keep doing this process of reduction. But I do need to see your division operations to the side of your page somewhere so I can keep up with what exactly you're trying to do so that you can get partial credit on your work whenever you make a mistake, should you make a mistake on this step. So let's go ahead. We're going to take 2 again. We'll divide it into 2, 7, 24. 2 goes into 2 once. 1 times 2 is 2. 2 goes into 7 3 times. 3 times 2 is 6. 2 goes into 12 6 times. 6 times 2 is 12. 2 goes into 4 2 times. So you get 1362 on top. And we should be able to go 2 into 4032. Suffice to say, guys, I hope I've made it clear that it's just a lot of work sometimes whenever you are actually trying to do this for, say, a problem where you've got 2-digit denominators. 2 goes into 3 one time. 1 times 2 is 2. Subtract, you get 1. Drop your 2 down. 2 into 12 goes 6 times. So 4032 reduces to 2016. And I should have been able to see that just by my eyesight, but you're going to keep going with this. You're going to keep going with this, guys. 2 into 2 goes 1 time. 1 times 2 is 2. 2 goes into 0 0 times. 2 goes into 1 0 times. And 2 goes into 16 8 times. So you should be able to reduce this to 1008. Which should be able to be reduced to 504, because 504 times 2 should give you 1008. And 504, if we reduced it by 2, that should be 252. 252 times 2 should give me 500. So let me do that. 2 times 252. I'm kind of skipping steps, guys, obviously. 2 times 2 gives you 4. 2 times 5 gives you 10. Carry the 1. 2 times 2 is 4. Plus 1 gives you 5. So yes, indeed, it would reduce to 252. And 252 should be able to be divisible by 2. Let's see. 1 time, you get 0. Drop your 5. 2 goes into 5 twice. Drop your 2. So 126 at some point. At some point, we get 126. And naturally, we would eventually be able to reduce that to 63, because 63 times 2 would, in fact, give you 126. Okay, so it looks like our denominator will eventually divide out into 63, assuming that our numerator also divides out. So let's go ahead. We'll keep dividing the numerator now by 2. 2 goes into 13 twice. 2 times, I'm sorry, not twice, 6 times rather. 6 times 2 is 12. 13 minus 12 gives you 1. Drop the 6. 2 goes into 16 8 times. 8 times 2 is 16. You get 2. 2 times 2 is 1. So you get 681 on top. 2 goes into 681. 2 into 6 goes 3 times. 3 times 2 is 6. Subtract, you get 0. Bring your 8 down. 2 into 8 goes 4 times. 4 times 2 is 8. Subtract, you get 0. Drop your 1 down. And unfortunately, we would not be able to divide 2 now into your denominator. So we would have to then erase, whoops, sorry, all of the other work, because it looks like we are now at a stopping point. So we found we had 681 all over, what was this? We had 2016, 1008. Okay, so we had 681 over 1008. 2 does not divide 681 anymore. 2 is divisible into 1008, but it is unlikely that any multiple of, say, 3 or something else would be divisible into 1008. So at this point, you might say that you are dealing with the most simplified fraction. Okay. And so how many steps do we have to take in order to get to this most simplified form fraction? How many multiplication steps did we have to take just to do this addition of subtraction problem? In fact, it was quite a bit of work, wouldn't you say? And so there is, in fact, a better way of doing this, which is what is known as the LCM, or least common multiple technique for adding fractions. But what the LCM requires you to do is it requires you to find the LCM of the denominators of the fractions you happen to be dealing with. So in this instance, if we were taking, say, 27 over 84, and we were adding it with 34 over 96, we would have to find the LCM, the least common multiple between 84 and 96. And so how do we do that? Well, we use prime factorization. And so we need to find the prime factors of 84 and the other denominator, 96. Go ahead, create a factor tree diagram because that's going to help you out in this problem. We know that 2 can divide 84 probably 42 times. 2 should be able to go into 42 21 times. 3 goes into 21 7 times. All right, so then now you need to go over to 96, find the prime factors of 96. 3 should be able to divide 96. 3 goes into 9 3 times. 3 goes into 6 2 times. So 3 times 32 should give you 96. All right, so now we need to divide 32. And 32 should be divisible by 2 and 16. 16 times 2 should give you 32, said another way. Because 2 times 10 is 20. 2 times 6 is 12. So 20 plus 12 gives you 32. And of course, 2 divides 16 and gives you 8. 8 is divisible by 2 and 4, and 2 divides 4. So if we were to list out all of the prime factors of 84, we would say that we have 2 times 2 times 3 times 7. And if we listed out all of the prime factors of 96, we have 3 times 2 times 2 times 2 times 2 times 2. All right, and so if we recall how we calculated the LCM, for the LCM, all you're looking for is you're looking for what you don't have in common between the two terms. And so what that requires you to do is to eliminate what you do have in common between the two terms. And so you're going to scan through this. I see I have a sequence of 2's. I'm going to cross them out once and write a 2 once. I see I have another sequence of 2's. I'll cross those out and write it once. I have a sequence of 3's. I cross it out, write it once. I have a 7 and a sequence of 2's left over. So I would need to, if I wanted to find the least common multiple, I would need to tack on to this multiplication problem a 7, a 2, and a 2, and a 2. And where are we getting that from? We're getting it from the fact that we have this sequence of 2's and the 7 left over that is not in common between the two terms. And so we're just tacking those on to the end. So now we have a big multiplication problem that we have to do. So 2 times 2 gives you 4. 3 times 7 gives you 21. 2 times 2 gives you 4, and you have a 2 left over. So then we would say that 4 times 2 is 8. So you'd have 8 times 21 times 4. 4 times 8 gives you 32. So we would do 32 times 21. Two times 1 is 2. 2 times 2 is 4. Drop your 0. 3 times 1 is 3. 3 times 2 is 6. Add everything together. 2 plus 0 is 2. 4 plus 3 is 7. And you have a 6 remaining. So you get 672. And this is your goal. This will be the common denominator for your two fractions. Now, just because it's your goal doesn't mean you're going to get to it easily. So in this instance, what we're going to do is we're going to rewrite the two fractions that we're dealing with. We had 27 over 84. We're going to give ourselves some space, and we're adding this with the other fraction, 34 over 96. So note that 96 was the same thing as 3 times 2 times 2 times 2 times 2 times 2. And what the 96 was missing was it was missing this 7 term. So what this tells you is you need to take 7 over 7 and multiply it on the top and the bottom of 96. Now, conversely, what the 84 was actually missing was the 84 was missing the sequence of 2's. 2 times 2 is 4, 4 times 2 is 8. So it was missing an 8 over 8. When you go and you multiply 7 times 96, here's the interesting thing. You should get 762 if we did our math correctly. And when we multiply 84 times 8, we're also going to get 762 there as well. So we don't even have to do the multiplication operation. We already know that the common denominator, assuming we did everything else correctly, should be 672. But by all means, go and check yourself. If we've done everything correctly up to this point, this should be our answer. However, now what we're going to do is we're going to do 27 times 8. 8 times 7, 8, 16, 24, 32, blah, 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 blah. What is it? It's 56. Carry the 5. 8 times 2 is 16 plus 5 gives you 21. So you should have 216 on top. And for 34 times 7, 7 times 4 gives you 28. Carry the 2. 7 times 3 is 21. Plus 2 gives you 23. So you should have 238. Adding across the top, you now have 216 plus 238 all over 672. And 216 plus 238. 8 plus 6 should give you 14. Carry the 1. 1 plus 1 is 2. 2 plus 3 is 5. 2 plus 2 gives you 4. So now you have 454 on top all over 672. Double check this addition, but it looks correct to me. So now you'll generally be left with a fraction that's much easier to manipulate. We're still not done because the fraction on the top and the bottom can in fact be divided by 2 because you're left with 454 on top and a 672 on bottom. So you can go ahead and take 2 and divide it into 672. 2 into 6 goes 3 times. 3 times 2 is 6. 2 into 7 goes 3 times. 3 times 2 gives you 6. Subtract, should get 1. 2 into 12 goes 6 times. So we would find that this will equal 336 in the denominator. 2 goes into 454. 2 into 4 goes 2 times. Subtract, yeah, drop your 5 down. 2 into 5 goes 2 times. Drop your 4 down. 2 into 4 goes 17 times. I'm sorry, 7 times rather. So you get 227 on top all over 336. And I believe this would be your simplest fraction if we've done everything correctly. Okay, so this is an example of how to use the LCM technique to get a much faster answer. And in my opinion, it was a much, much faster answer. Was it still a decent amount of work? Yes. But look at how many steps we had to go through here. Look at how many multiplication steps you had to do. Look at how much more involved the addition was because you have 4-digit addition problem. And then you had a ton of division problems, and we still weren't at our final answer. We had gotten 681 all over 1008, and we were not even finished there. It was possible that we could still reduce it. In fact, we should have been able to reduce it to 227 all over 336 unless we had made a mistake, which By the way, if you consider how easy it is to make a mistake with one of these addition, multiplication, or division problems, and the fact that we have to do each one of these correctly in order to correctly reduce our fraction in the first place, I hope you can see that you're much more likely to make a mistake if you had used the multiply by the opposing base method as opposed to using the least common multiple technique for adding the two fractions together. Yes, the least common multiple technique does in fact look like magic the first couple of times you use it, and it's hard to convince yourself that without practicing and practicing and practicing, that in fact the answer you're getting using the least common multiple technique will in fact be the same thing. However, practice with this technique, understand it's available, and if you use it in critical moments, such as when you have fractions that have two digits in their denominator, you are going to find that your life will be much easier than if you don't use the LCM technique. Let's have another example of how to use the LCM. Suppose we have 17 over we'll say this is 50 plus 32 over, we'll say this is 150. Okay. Actually, we won't do it. That's too easy, right? We'll do 125. Do a little bit more challenging. Do 125. Okay. Now, if you had used the multiply by opposing base method, I hope I've convinced you guys that it's going to be kind of a pain in the ass. Instead, if we use the LCM technique, we can, in fact, simply find the prime factorization of 50 and 125. And that's not too bad to do, or it's not too hard to do, because 50 is divisible by 2, and you'll eventually find that the prime factorization of 50 is 2 times 5 times 5. The prime factorization of 125 is fairly straightforward as well. Turns out that 5 times 25 is going to give you 125. And of course, 5 and 5 gives you 25. And so, just stacking our prime factors up with each other, and then considering what happens now, you're going to see that you have a set of 5s in common, have another set of 5s in common, and all you're missing really is a 2 on the top and a 5 on the bottom. 5 times 5 is 25, times 5 will be 125, times 2 will be 2 times 125. Sorry. 2 times 5 gives you 10, carry the 1. 2 times 2 is 4, plus 1 gives you 5. 2 times 1 is 2. So you should find that 2 times 125 should give you 250. And I should have known that. This is our goal. And in fact, if we do everything correctly, this will be our common denominator. So we're going to take our first fraction, which is 17 over 50. And what we're going to do is we're going to multiply this fraction very, very carefully by what's going to allow us to get to 250. And this might at first seem a little bit challenging to guess what would allow us to get to 250. But in fact, you just have to look here to this second prime factor, where you see that what 50 is missing is it's missing a 5. It needs to have 5 multiplied by this row in order for it to get to that LCM of 250. And so what that tells you is you need to take this first fraction, 17 over 50, and if we want that denominator to magically become 250, we've got to multiply the top and the bottom by 5, and then vice versa for 125. You'll see that the 125 is missing the 2 term. If you had multiplied 2 by 125, you're going to get 250. And so you don't really do anything with the initial fraction 32 over 125, but you are going to give yourself some space, and you're going to multiply 2 over 2 on the top and the bottom. So now, at the end of the day, you should be left with two fractions. You'll be left with two fractions that have 250 in the denominator. But you only have to do 2 more multiplication operations. You're going to do 17 times 5. 5 times 7 gives you 35. Carry the 3. 5 times 1 is 5 plus 3 gives you 8. So we have 85 on the top. 32 times 2 should give us 64. 2 times 2 is 4. 2 times 3 is 6. And of course, we can, at this point, add across the top. So 64 plus 85. 4 plus 5 gives you 9. 6 plus 8 gives us 14. So we should have a 149 all over 250. And I believe that this is as good as it gets because 2 does not divide 149. 2 does, in fact, divide 250. 5 divides 250. 2 divides 250. But because none of the prime factors of 250, i.e. 5 and 2, will divide 149, we can say with confidence that this will be our most simplest form. So just to repeat for students who are a little bit iffy on fraction reduction, you only have to check for fraction reduction, just write this down, for fraction reduction, you only have to check one thing. If the prime factors of the denominator divide the numerator. That's really the only thing you have to check, guys. If the prime factors of the denominator will in fact divide the numerator, then you can reduce. That's the only time you're actually allowed to reduce, is if the prime factors will divide the numerator. And students might say, well, what about if it's a case where, say, 250, which is our number in the denominator, would divide some number that's in our numerator? Like maybe in this instance, 250 certainly doesn't divide 149, but suppose we had a different number in our numerator, would this rule still hold true? And the answer is yes, this rule would still hold true, because any of the prime factors of 250 will in fact divide 250 itself. So if 250 goes into something that exists in the numerator, then its prime factors will also divide that something that's in the numerator. So said another way, if what we're doing when we simplify is we're checking to see what number divides both the numerator and denominator, all we got to do is we check the prime factors of the denominator or vice versa. In this case, it's a lot easier for us to check the factors of the denominator given that we already know the prime factorization because we calculated it over here with the LCM. And so since we know it was only two numbers, 2 and 5, that's all we've got to check in order to simplify the numerator. I hope that makes some sense, but if students are a little bit fuzzy about that, come see me in my office hours. I will definitely explain it further. To that end, I will see you guys in class.